Welcome to lecture 40 on essentials of topology. In this lecture, we will continue the study of the theory of connected topological spaces. In the previous lecture, we have studied the connectedness of set of real numbers and its subsets. In this lecture, we will use these concepts to discuss the existence of non-constant continuous maps as well as non-homeomorphic spaces. The first concept which we will discuss is existence of continuous functions. Note that when we are talking about the existence of these continuous functions, our motive is to discuss about non-constant continuous functions because we already know that constant functions are always continuous. In order to discuss this theory, we already have studied that if we have a continuous function from a topological space x tau to y tau dash, this function is continuous and the space is connected. Then its image, that is f of x, is also connected. Now, if we are taking a function from this real line with Euclidean topology to a topological space, let us take y tau dash. Note that this R is connected and the subsets which are connected are intervals. If we can construct a continuous function, what feature should this function have? This function should map these intervals to a connected subset of y, that is, if we are taking an interval I here, this is an interval, what should be f of I, that is a subset of y, and note that this should always be connected. In case it is disconnected, this function cannot be continuous function. Having this idea, begin with this example, which is any continuous function f from R to Q must be a constant function. It means that we cannot construct any non-constant continuous function from this set of reals to set of rational numbers, which we can see here. Whenever we are talking about this R, meaning is that R is with Euclidean topology and this is a subspace of this topological space. Now note that constant maps are always continuous, so there is no problem regarding this statement, but question is we cannot construct any other map. Now if we are taking a non-constant map from R to Q, this is not a constant map, and if this is not a constant map, what about the image of R? Obviously this is subset of Q and the cardinality of this set will be greater than or equal to 2. Recall that we have shown that this set is totally disconnected, and if this is totally disconnected, only singleton sets are connected here. This is connected for all x belongs to Q. It means that this f of R is disconnected. While we have shown that this is connected. This is connected. So what is happening here? We have assumed a non-constant function here. If this is continuous, then image of R should also be connected, but note that if the function is not constant, the image of R under F is always disconnected. So we cannot construct a non-constant continuous function from set of real numbers to set of rationals. What we have justified here, we have used the fact that this Q is totally disconnected, and that concept we have used to justify that we cannot construct a continuous non-constant function. The same concept can be extended to other topological spaces. For example, question is, can we construct a non-constant continuous function from a real line with Euclidean topology to real line with lower limit topology? Answer is no. We cannot construct any continuous function. Why? We have already seen that real line with lower limit topology is also totally disconnected. Even if we are talking about real line with Euclidean topology to real line with, let us take discrete topology. Question is, can we construct a continuous function from R to R with these topologies which are not constant? Answer is no. Why? Because this topology or this space is totally disconnected. Moving ahead, we have two questions with us. The first is how to check that the given topological spaces are homeomorphic. It is it can be answered easily, and what we have to do is that if we can construct a homeomorphism from this topological space x tau to another topological space y tau dash, if we can construct it, we can say that the topological space x tau is homeomorphic to the topological space y tau dash. But question is how to check that the given topological spaces are not homeomorphic. This is not easy to justify that there does not exist any homeomorphism from this space to this one. Question is, in that cases, what to do? Connectedness help us at some point. How the connectedness is helping? Let us see an example. Here we are taking this set closed interval 0 3. Let us take this is x, and now let us take a set y which is union of these two intervals 0 1 and 3 4. They are subspaces of this real line with Euclidean topology. It is to be noted that this set is connected and this is an interval. What about this set? This is not connected. Why? Because this is not an interval. So, if there is any homeomorphism from x to y, if we are taking there is a homeomorphism from x to y, note that we have already taken that this is connected. So, this should also be connected. But it is not in this case, and therefore we cannot construct any homeomorphism from this interval, that is closed interval 0 3, to the union of two intervals, that is closed interval 0 1 and closed interval 3 4, and therefore this interval 0 3 is not homeomorphic to union of these two closed intervals. Having this idea in the mind, let us discuss about some of the non-homeomorphic topological spaces. But before studying them, let us take a simple result, and this result is given like this one. That is, if we are having a function f from topological space x tau to y tau dash, and this function is a homeomorphism. Now let us take an element a in x and take a subset x dash which is x minus of a. Let us take another set y dash, that is y minus of fa. Then what we can justify that this x dash with relative topology and this y dash with relative topology is also homeomorphic. Meaning is to say that if we are taking this is the set x and this is the set y, what we are doing that we are taking an element here, that is a, and we are taking its image, that is f of a. Now if we are removing these two, and after removal of these from x to y, we are getting a new set that we have taken as x dash. This is x minus of the singleton set A, that is obviously a subset of x, and we have also got a set y dash which is y minus of this singleton set fa, that is subset of y. Now we can talk about the relative topology on x dash with respect to the topology on x, and similarly we can talk about the relative topology on y dash with respect to this topology, that is tau dash. If we want to justify that these two subspaces are homeomorphic, it's easy to justify because if we are taking a function g from x dash to with topology tau x dash to, let us take the space y dash, and with the topology on it, that is tau dash y dash, this function is defined as gx is equal to fx for all x belongs to x dash. Note that this g is bijective as f is bijective. Even what we can say that this function g is nothing but the restriction of f over x dash, that is g is a restricted function. So g is bijective. We know that restricted functions are continuous, so g is also continuous. G inverse is continuous too because that can be visualized as a restricted function, that is f inverse over y dash, and therefore this G is a homeomorphism, and hence this topological space is homeomorphic to this one. Now let us use this result to show that some of the topological spaces are not homeomorphic, that is, there exists no homeomorphism between these spaces. We are taking examples as intervals. Note that these intervals are taken as a subspace of real line with Euclidean topology. Let us begin with the first one. We want to show that this open interval AB is not homeomorphic to the semi-open interval CD. In order to justify it, let us see, or let us begin with, if possible, assume that this open interval AB is homeomorphic to this semi-open interval CD, and if it is, then there exists a homeomorphism from we are taking this CD to this open interval AB, and note that this F is a homeomorphism. Now, if this is a homeomorphism, then from the previous result, what we can conclude from here that if we are removing a singleton set C from this interval, this should also be homeomorphic to this open interval AB minus f of C. Note that this f of C will lie in this open interval AB. Now, this semi-open interval minus of the singleton set C, this is precisely the open interval CD, and this is open interval AB minus some y, and this y is nothing but f of c. Note that this one is connected because this is an open interval, but this is disconnected. This is a contradiction, and therefore this open interval AB cannot be homeomorphic to this semi-open interval CD. Even we can show that this open interval AB cannot homeomorphic to a closed interval CD where these A, B, C and D are real numbers with A is less than B and C is less than D. Similar to the previous one, that is how we have shown that this open interval AB is not homeomorphic to this semi-open interval CD. Again, if we assume that this open interval AB is homeomorphic to this closed interval CD, let us assume it, and if it is so, then there exists a homeomorphism F from this closed interval CD to this open interval AB. This F is a homeomorphism. Now, if we are removing this C from this closed interval CD, that is CD minus of C, this should be homeomorphic to this open interval AB minus of F of C, this singleton set, where F of C belongs to this open interval AB. Again, this is nothing but a semi-open interval CD, which is homeomorphic to AB minus of singleton set Y, where Y is equal to F of C. Again, note that this is connected, and what about it? This is disconnected. Why? Because this is not an interval. Therefore, we reach to a contradiction again. Thus, this open interval AB cannot be homeomorphic to closed interval CD. Finally, let us take this example, that is, this semi-open interval AB is not homeomorphic to closed interval CD. Begin with, if possible, let us assume it, that is, this semi-open interval AB is homeomorphic to this closed interval CD. It means that there exists a homeomorphism from this closed interval CD to this semi-open interval AB. And this is semi-open interval AB, and this is F is a homeomorphism. Therefore, the result which we have already discussed, if we are eliminating this singleton set C from here, this will be homeomorphic to this semi-open interval AB minus F of C, where this Fc is an element of this semi-open interval AB. That is, this CD, that is semi-open interval, is homeomorphic to this semi-open interval AB minus of the singleton set X, where X is equal to F of C, which is a member of this semi-open interval AB. Now, if these two are homeomorphic, it means that there exists a homeomorphism. Let us take that homeomorphism is G from this semi-open interval CD to this interval AB minus of this singleton set X. And again, if we are using the result, what we can conclude that if we remove the singleton set D from this semi-open interval, this should be homeomorphic to this AB minus of this singleton set X, and this is minus of image of D under this function G. or this is semi this is simply open interval CD. This will be homeomorphic to this semi open interval minus of this set xy where y is equal to g of t. It is to be noted here that x cannot be equal to y here. Now this interval is connected, but what about this one? This is a semi-open interval, this is A and this is B. Now if we are removing two elements from this interval, either this A or any other or any two elements from inside this interval, this will always be disconnected and therefore we reached to a contradiction. Hence, this semi-open interval AB is not homeomorphic to closed interval CD. These are the references. That's all from this lecture. Thank you.